This is the third installment in a series on the structure and function of the urinary system that follows along with the Marieb Human Anatomy and Physiology text published by Pearson, Benjamin Cummings. Last time we talked about the forces that govern filtration in the glomerulus of the kidney, the place where all that water escapes from the blood into the renal tubule, into the capsule and renal tubule that mainly has to be reabsorbed in order to maintain homeostasis in the body. Huge amount of filtration, 99% reabsorption, and then we excrete a small volume of urine, relatively speaking. So today what we're going to start out talking about is what is it, how do we regulate the rate of filtration in the glomerulus, in the 2 million or so glomeruli of the two kidneys, and which in turn will determine the rate of urine production and the volume of blood as a consequence. He said the two things that we can do to regulate the rate of capillary or glomerular filtration is to constrict or dilate the afferent arterioles leading into the glomerulus, or constrict or dilate the efferent arterioles as the blood is leaving the glomerulus. And by those two mechanisms, we can control the hydrostatic pressure in the glomerular capillaries. That's the variable. That's the force that drives water out, and it's manageable. We can alter that pressure. We can control that. That's how we get at changing glomerular filtration rate. All right, so some built-in mechanisms first to control glomerular filtration rate called intrinsic factors. We're going to try to make sure that the filtration rate is requisite with a normal, healthy condition, and if it begins to change for some reason, we're going to bring it back in line. And then we'll talk about some outside forces, some things happening in the body that are going to affect glomerular filtration rate and override essentially these intrinsic factors or controls. So the intrinsic controls, you could also call them autoregulation. We talked about autoregulation of blood flow in all the organs when we talked about the cardiovascular system, and we, for example, talked about metabolic autoregulation. Each organ determines its own blood flow according to its metabolic needs. Now we're talking about autoregulation of glomerular filtration rate. How fast are we forming urine? How is that going to impact blood volume and blood pressure? So one part of this autoregulation story is actually the exact same as we talked about when we talked about the cardiovascular system, myogenic autoregulation, a reaction to changes in mean arterial pressure by the arterioles themselves, in this case the afferent arterioles, and also tubuloglomerular feedback. So let's see what in the world those things are. Okay, the myogenic mechanism, just to review, again, we've already seen this, but it's never a bad idea to revisit something in physiology, to nail it down and make it familiar again. If the blood pressure changes, that pressure coming to the glomerulus, to the afferent arteriole, it's going to change the amount of stretch in the walls of those afferent arterioles, and when that happens, the smooth muscle cells of the arteriole will respond. In other words, if mean arterial pressure rises, those arterioles are going to become stretched. The pressure coming in is greater. The pressure downstream in the glomerulus would be greater, and the filtration rate would go way up. A way of dampening out some of that rise in filtration rate is this myogenic response. The smooth muscles in the afferent arteriole will constrict, the cells will constrict or contract when they sense that stretch. You stretch them and try to drive more pressure in, they immediately respond by constricting or contracting. No signaling method, no negative feedback system. You stretch them, they contract. What that does is limit the amount of that extra mean arterial pressure that will push its way into the capillary. So when the blood pressure goes up, filtration rate does go up, but not as much as it would have because the arterioles automatically constrict down. So it dampens out what would be a rise in glomerular filtration rate, rise in hydrostatic pressure and filtration rate. On the other hand, if the mean arterial pressure falls, we become dehydrated, for example, those afferent arterial smooth muscle cells will not be stretched as much. They're not getting as much of that blood pressure hitting them, and they will just dilate. So if the blood pressure goes down, the glomerular hydrostatic pressure would go down and the filtration rate would go way down. But it doesn't go down as much because this afferent arteriole dilates and lets more of that mean arterial pressure in and pushes the glomerular filtration rate back up towards normal. It's definitely going to go down, not as much. So this is a way to blunt or dampen changes in capillary pressure in the glomerulus and filtration rate with changes in mean arterial pressure and blood pressure. The myogenic mechanism. Okay, this is an entirely different mechanism that we have in addition to that. It's called the tubuloglomerular feedback mechanism. Something in the tubule is going to happen that's going to talk to something and make a change of something happening in the glomerulus that's going to affect filtration rate. So let's take a look at what's going on here. We said that each renal tubule forms a convoluted proximal tubule, a loop of Henle, a convoluted distal tubule, and then returns right back to the same corpuscle from whence it arose. So this little circle represents a cross-section through the thick ascending limb of the loop of Henle when it arrives back at its own original glomerulus, its only original juxtaglomerular apparatus, it's correctly called. And in that section of the tubule are macula densa cells that can sense the concentration, the osmolarity, the salt concentration of the filtrate. How are things coming along with the processing of our filtrate? So if the macula densa cells sense a drop in salt concentration, they're going to interpret that to mean that the filtration rate is too low. So watery filtrate coming to the macula densa suggests a slow processing, a low GFR or glomerular filtration rate. More salt is being reabsorbed because the fluid is traveling slowly through the tubule and it's getting more and more dilute. So anyway, if the salt concentration of the filtrate is going down, as sensed by the macula densa cells, they will cause the afferent arterial smooth muscle to dilate, let more pressure into the glomerulus, and increase the glomerular filtration rate. Macula densa cells believe the filtration rate is too low. They'll raise up the GFR or glomerular filtration rate by causing the afferent arteriole to vasodilate. So that's one way that they can correct this problem of a low GFR. Also, they can talk to the granular cells or juxtaglomerular cells and cause them to release renin. And this brings into action one of the coolest things about the nephron entirely. The release of renin from the juxtaglomerular cells will lead to the production of angiotensin II, as you well know. Renin is an enzyme that modifies angiotensinogen in the plasma, cuts off a piece of peptide, forming angiotensin I. And angiotensin I is a protein or peptide that then, when it circulates through the lung epithelium, the lung endothelium, is converted to angiotensin II. Angiotensin II is a vasoconstrictor, as you know, but here's a cool thing. Angiotensin II selectively constricts the efferent arteriole. Now, angiotensin II in the systemic circulation as a whole causes vasoconstriction and raises the peripheral resistance, raises mean arterial pressure. But here in the kidney, at the juxtaglomerular apparatus, it causes constriction specifically of the efferent arteriole. And if you can imagine, again, constricting that efferent arteriole, it's going to raise that hydrostatic pressure in the glomerulus and also contribute to elevating the GFR, making the filtration rate go up. So we started out with a watery filtrate, Maculodensa cells felt it was a low GFR. They caused afferent vasodilation, which raised hydrostatic pressure and filtration rate. They caused renin release, which produced angiotensin II, which caused efferent constriction, which raised the hydrostatic pressure and drove up the glomerular filtration rate. Incidentally, angiotensin II has also, as we said, raised the mean arterial pressure coming into this system, which in itself a third way that will raise up the hydrostatic pressure in the glomerular capillaries and raise the filtration rate. So the opposite is also true. What if the filtrate was getting saltier and saltier? The maculodensa cells would interpret that to mean, I guess I didn't write that out in that way. The maculodensa cells would interpret that to mean that GFR is too high. The flow rate in the tubule is so high that we can't reabsorb the normal amount of salt, and the salt concentration of the filtrate therefore is rising. In that case, the maculodensa cells would cause afferent constriction, reducing the net filtration pressure by reducing the hydrostatic pressure and reducing the glomerular filtration rate. They would cause the juxtaglomerular cells to release less renin. The angiotensin II levels would go down, and the efferent arterioles would dilate and lowering the hydrostatic pressure in the glomerular capillaries, contributing to a drop in GFR. So the maculodensa cells will orchestrate this tubuloglomerular feedback by controlling the smooth muscle of the afferent arteriole and the release of renin, or inhibition of release of renin, by the juxtaglomerular cells. There it is. I did write it all down. All right, let's move on and talk about extrinsic influences on glomerular filtration rate. Epinephrine and norepinephrine we've known for a long time as part of the autonomic nervous system cause vasoconstriction of arterioles and veins, and the net effect is an increase in total peripheral resistance, increase in mean arterial pressure, among other things that they do. We said that one effect of that is going to be to redistribute blood flow from some organs by causing vasoconstriction, reducing their flow, so that that blood flow, that part of the cardiac output, can then be delivered to the working muscles during exercise or during some dramatic response to a challenge. One of the organs that we always mentioned was the kidneys, and in fact, epinephrine and norepinephrine cause afferent vasoconstriction in the kidneys. So epinephrine and norepinephrine work here in the afferent arteriole, so that when sympathetic nervous system is activated, it's going to constrict that afferent arteriole, and it's going to reduce the net filtration pressure, reduce the glomerular filtration rate. However, these hormones also stimulate renin release. And so renin release produces angiotensin II, which we know also elevates mean arterial pressure, which is good for the exercise situation, increased total peripheral resistance, but in this case is going to help us out. We don't want to cut off glomerular filtration and urine production altogether during exercise. The angiotensin II will constrict the efferent arterioles, trapping some of the pressure in the glomerular capillaries and compensating, raising the capillary filtration rate up a little bit so that we don't utterly stop producing urine during sympathetic nervous system activation. It also turns out that constriction of the afferent arterial smooth muscle by the sympathetic nervous system will stiffen things up there such that the juxtaglomerular cells interpret that to mean, oh, the blood pressure is low. And so they will release some extra renin in addition, which will cause angiotensin II to be produced, increasing glomerular filtration rate. So we have a big drop in filtration rate as is initiated by the epinephrine and norepinephrine during sympathetic activation. Then we have some compensatory responses involving angiotensin II production and efferent constriction, which will bring the filtration rate back up somewhat. It will definitely be curtailed during exercise, but not utterly discontinued. So I just pulled together a slide here reviewing 3 different ways that the renin-angiotensin system may be activated. The sympathetic nervous system directly signals release of renin by the juxtaglomerular cells. That we've known about since chapters 16 and 19, and we're just summarizing it here again. We just mentioned it as an extrinsic control. That will cause release of renin and production of angiotensin II. Now we know that the macula densa cells, when the GFR is too low and therefore the salt concentration of the filtrate is too low, can cause the juxtaglomerular cells to release renin, which will raise the mean arterial pressure, as well as that angiotensin II will cause efferent constriction and raise the glomerular filtration rate. And finally, reduced stretch of granular cells. They are the pressure sensor, the blood pressure sensor of the kidneys. Reduced stretch of those granular cells will cause renin release. That's the original thing we talked about with respect to the renin-angiotensin mechanism. If blood pressure goes down, kidneys sense low blood pressure. Granular cells, we now know, release renin, form angiotensin II, and raise the blood pressure back up. So those are 3 ways that we can talk to those granular cells and control their release of renin, which forms angiotensin. We should not forget that whenever we produce angiotensin II, we also produce aldosterone, and in a later section of this series, you'll see how aldosterone, where in the nephron aldosterone actually works. It turns out it's in the distal tubule to increase reabsorption of salt and water. There are a few other things that are now known to affect glomerular filtration rate. Prostaglandin E2, for example, may be the signal that's released by the macula densa cells that causes the juxtaglomerular cells to release renin when GFR is too low. So there's a few other things, but I think we have enough on our plate. If you can just remember the regulation of GFR by the myogenic mechanism, tubuloglomerular feedback, and the extrinsic effects of sympathetic nervous system regulation of blood pressure and consequently glomerular filtration, I think we'll be in good shape. The next section of our discussion will be one describing how the reabsorption occurs in the nephron. What reabsorption processes take place in the proximal tubule, the loop of Henle, the distal tubule, and finally the collecting duct. So that will be the subject of the next couple of sessions.